Hi, welcome to Mathematics with Tom. I am Tom, and we're going to do just one proof today, one proof. And this is based off the work, and we did it in our previous video. And what it was is we took a look at the exponential shift on the product of an exponential and some differentiable function x. And we found that if you just have the first derivative of it, it gives us the shift of d plus a right here. We took a second derivative and it shifted it by this and then multiplied the shift to the second power. If we took a third derivative, we found the shift was cubed, and the nth derivative, the shift is raised to the nth power. So we're going to use those three pieces of information. We're going to use them one more time to write one more proof. So here we go. Let's come over here. And what we're going to do is show that the polynomial of d e to the at acting on x is equal to e to the at, the polynomial shifted by d plus a. The whole thing is shifted times whatever our function of x is. Okay? So let's do this. Recall this. So we need a quick recall. Recall that we said that the polynomial of d is equal to, it was equal to d to the nth power plus c to the c sub 1 d to the n minus 1, and if you continue this pattern, it takes a polynomial pattern, and down we get to where we have plus cn minus 1 d plus cn. Okay, so that was our polynomial of d, and now what we're going to do is we're going to apply this entire polynomial of d to our product of the exponential times a differentiable function. Let's see if we can end up with our shifted function. Let's try. So here we go. We'll start I'm going to start. So I'm going to start here on the left-hand side of the equation, and then we'll see if we can end. This is our goal, our mission, if we choose to accept it, is to end on the right-hand side. Okay. So I'm going to take P of d, e, a, t, x. First thing is, let's expand out what it means to be the polynomial of d. Well, that means that we're just going to use this. We're going to use what we know about the polynomial of d. So that's d to the n plus c1 d to the n minus 1 plus dot. We can keep going. We're going to write this all the way out. Cn minus 1 d plus Cn e to the atx. Now, let's distribute our function here, our function e to the at times x. So I have dn e a t x plus c1 d n minus 1 e a t x plus dot 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 plus cn minus 1 d e a t x plus cn e a t x. Okay, I know that's a lot to write, but it's good practice to see the pattern develop. At least I think so. This dn e a t x, that we have over here. So let's go back, just make a quick reference. This right here, dn e a t x is e a t d plus a n x. That's what we had shown previously. So let's come back and let's apply this. So if we apply that, this is going to give me an e a t d plus a raised to the nth power x plus C1 D, oops, no, not that, not that. This is where you go grab an eraser, which I have one right here. Fix that. This is C1 E A T D plus A n minus 1 x plus, you continue this pattern, and we're almost done. This is Cn minus 1 E A T D plus A. This is just the first power now. This is the, notice if it was the n minus 1 derivative, the shift is raised to the n minus 1. And here we're taking the first derivative, our shift is raised to the first. X plus Cn E A T x. Okay, our last step is to factor. Let's factor this. So this is equal to, I'm going to factor in e to the at out of every term. So this is going to be a d plus a to the nth power. Now let's also do this. Let's factor, notice I have an x in every term also. Let's factor that x out, but we're going to move it and put it over here on the right, because we were kind of trying to look at where we're going. We're trying to end here, and it looks like we're getting kind of close. So let's factor that x to the right. So my next term is plus C1 d plus a n minus 1 plus, and you keep applying this, you keep applying until you come all the way down to the c n minus 1 times d plus a plus cn, and then the x goes on the right-hand side. But look at this. This is a polynomial. This is just the variable raised to the nth power, the variable raised to the n minus 1 power, and so on, the variable to the first power, the variable to the 0 power. Well, we already gave this a name. We gave that a name. This was very simply, this whole piece is polynomial in d plus a times x times e to the at. Okay. And this is the proof for the exponential shift applied to our polynomial of d. All right? Thanks for watching.